Alright, so this is the last semblance of any lecture for the semester in this class. We're just going to go over the review for exam 3. And hopefully, if I've done things right, then this will be the easiest final that you have this semester. So, my apologies if I missed on that, but it should be reasonably easy. Hopefully, none of you are stressing about it. So, okay, for this first problem, we're looking at the harmonic sequence here, and it famously diverges, and so this is asking to demonstrate that using induction. So the pattern that I want you to get into whenever you go through inductive proofs is to identify a base case, and then through the inductive hypothesis, apply the inductive step. Right, and so the let's see, a journey of 1,000 miles begins with a single step. Right, so that would be the base case, and then to show that you can get there, you have to apply a right step after a left step, or a left step following a right step. And if you can do that, and you take that first step, then you can go 1,000 miles or further, right? And so that's the idea of induction. So our first step is to use the base case. So here the variable. So up here it's a little confusing because k is here and here, but here we're substituting 2 to the p for k, right? So we're not inducing k, we're inducing p. Right? So at p0 we have h sub 1, right? So it's 1 on the left hand side and 1 on the right hand side, where p is 0, right? And then, okay, so it holds true, greater than or equal to. It's equal to in this case, but beyond p equals 0, this turns out to be strictly greater than for the left hand side. So we assume that we can continue to take another step following our previous one, right? So given that we have already taken a step, we want to show that we can take another step, right? So h sub 2 to the p plus 1, right? So then we put it over here on as the superscript for the summation, and then as we tend to do with these summations, whenever we're trying to identify some property, we pull out a convenient number of terms. So because we want to use the inductive hypothesis, which is just an algebraic substitution, we need to have the presumed equality, the presumed value on one hand, and the other terms somewhere else. So we pull out half the terms, so 2 to the p terms, and then we show that in this case we have greater than or equal to, I think because for p equals 1 we would have equality, but we show that these where the denominator continues to increase, each of these terms is getting successively smaller. As the denominator increases, the value of the fraction decreases, right? So a quarter is smaller than a half, right? So we take the largest denominator, or the least valued fraction, and we apply that as a substitution for every one of the terms in this portion of the sum, and we establish that without that substitution, without replacing it for the least value, then that sum is greater than whenever we are adding up just the smallest values, right? But with that substitution, we gain the ability to simplify. So now this portion of the sum, where we have 2 to the p terms, becomes 2 to the p over this now common denominator. And this simplifies to just 1/2 pretty nicely, right? And so we've set aside this summation here until this point. So now that we have 1/2 here, we can finally address this. And via the inductive hypothesis, we apply our substitution, and this is exactly what we're assuming, right? So if we were able to take a left step, we now want a right step, or if we were able to take a right step, we now want a left step, right? In our journey of 1,000 miles, we make that substitution, and we say, okay, well, if it held true here, then it'll hold true for another step. Just look, right? And we substitute it in, and now this 1/2 and the p over 2 combines to p plus 1 over 2, and this is exactly what we were trying to prove, right? So with that, we're able to establish that as p goes to infinity, this sum goes to infinity because there's nothing suppressing it. There's nothing driving it to 0. So it diverges. The harmonic sequence diverges. Okay, so the second one is trivially true, or trivially true, just by observation, but is an excellent chance to practice induction. For old time's sake, right? It's the same pattern, right? So even something that's trivially simple, you can still demonstrate that it's true. And as I've mentioned before, like some of the hardest proofs are of things that we've always taken as true, but we want to be able to establish these as results of some other truth, some lower level axiom. So in this case, we'll go ahead and establish it again, right? So in the base case, we show that when n equals 1, we have that 1 is less than 2 to the 1. So 1 is less than 2. Okay, great. So if we're given that it's true for some value n, then it'll hold true for n plus 1, right? And again, we have the base case, and then we begin the inductive step. So here we have n plus 1, and then right off the bat, we can make our inductive hypothesis, our substitution by the inductive hypothesis, so that n is less than 2 to the n, right? We're assuming that it held true for the previous step, and when it's true for the previous step, it's true for the ensuing step. So we make the substitution, and we still have this lingering plus 1. Well, 1 is less than 2 to the n, already. So we make that substitution, and it's a strict less than there. And now we have two like terms, we combine them, and we get 2 to the n plus 1. So it holds for all n greater than or equal to 1. Okay. So now, yes, I'm introducing a problem where we have to define a recursive function. And what I wanted to get at here is that you need some initial definition, some initial value for whatever the beginning of your range of definition is. So I call it a halting condition here, or a halting criterion. And you will need that in any recursive function you define programmatically, otherwise you'll get a stack overflow exception. And you will get one eventually. If you code long enough, you'll make a mistake, and that'll be kind of how it gets drilled in. But when that happens, when you get a stack overflow exception, it means that you haven't properly defined your halting criterion. So all I'm asking for here is a two-part definition, right? So some initial condition for some minimal value of whatever your input variable is. So here it's f of 0, and then the recursive definition. So how we define f of n in terms of f of n minus 1. Right? So for this sum, whenever k is equal to 0, then we have that f of 0 equals a. And then whenever k is equal to something larger, we use n. I suppose I could have used k, but whatever. Then f of our input variable is equal to f of n minus 1 plus a. Right? And it's because we're adding the same term over and over again, from 0 all the way up to k or n, whatever. I'm going to defend this, right? I feel like n is a valid choice for this. That's really what we're looking at here. Right? Anyway, it doesn't matter. So this one is very simply defined. All I'm looking for in a recursive function is the initial conditions, right? The initial criterion, the halting criterion, and the recursive definition. So you have a term defined in one or more previous terms, but in this case we're only using one. Right? But in Fibonacci, there's two terms. And in that case, there's two initial conditions because you need to be able to satisfy looking back 2 steps instead of 1. So, okay. So now the second part, counting. This this is an extremely simple problem. I imagine many of you could solve that before you came into my class. But if you have 1,000 servers and each server has 24 USB ports, then how many are there? Well, this is the product rule, right? So 24 times 1,000 is 24,000. Okay, there is no trick there. It is extremely simple, right? But again, we're taking fundamental principles and using them to derive more meaningful results. Okay, so now you have a set A consisting of 32 elements, then how many possible subsets are there? And so we mentioned it in class that the inclusion of an element is binary. Either it's present, in which case we can represent it as a 1, or it's not present, in which case we can represent it with a 0. Well, if you're representing 32 elements with 1s and 0s, that's a binary string. It's a bit string of length 32. And so there are 2 to the 32 possible values for a bit string of length 32, right? And so that's 4,294,967,296 distinct values. So so because of this this one-to-one relationship between a binary string and the inclusion of elements from a master set, then this 2 to the n relationship ends up being the number of possible subsets from a master set. So so that's our answer. This would have been sufficient for your answer. So, but the explanation is there for your benefit. Okay, so we have a sprint where we have one racer that is much faster than everyone else, and so in this case, the race is really for second and third place. And so in this case, we have a diminished field where there's only really 7 racers competing for the 2 available spots, right? Silver and bronze. So there's 7 ways to pick the second place finisher, and once you've selected that, there are 6 remaining racers that could finish third. So again, it's the product rule, 7 times 6. And then some of you would notice that this is also an R permutation, right? And so in that case, we can use this notation where the field is 7 and there are 2 spots, 2 variables, given if we are given that the winner is going to be a particular racer. Okay. So that would be 7 factorial divided by 7 minus 2 factorial, which is again 7 times 6, and it's 56. And then the bonus problem, which is more applicable to those of you that are eager to get started in the professional world of software development. It starts with practice, right? And so the command is this. This is the correct answer, right? and there may have been additional templates or anything that you could define, and I would have accepted that. But this command will take the project, it'll name the project after whatever the current directory is. I included these additional commands. So this is really where you would name your project. There might be an optional input where you can name the project something else. And you can certainly go back and rename it later if you want. But this is the answer. And for those of you that are interested, I will be posting in a new playlist a run through of the project where you can create it as well. It's not so much a tutorial series. I'll go back and add some comments that'll explain what everything is for those of you that want to fine tune it and so forth. But it's more of a challenge. I want to see, and please do if you can. I want to see if any of you are able to run through it faster than I am. It's a challenge. I'm trying to think of what a possible reward could be for anyone that I guess types fast enough to beat me in this particular race. If you are able to find a screen recorder, open broadcast software, OBS is what I'm using to screen capture these lectures. Record it, post it, email me the link, and for the first person that's able to beat me in each category, then I will come up with some sort of follow-up to reward your efforts. I'm not exactly sure what that'll be. Prepare to be disappointed on the prize, right? Other than bragging rights and calling, commenting on it and letting the world know that you beat me. But so hopefully it'll be a fun challenge. But really, what I'm getting for is that through the repetitive action, that it'll drill in these fundamentals, and most importantly, get you to the point that you don't feel any intimidation at starting a project, and when you do start a project, and when you have an idea that you're excited about, that you're able to really hit the ground running, and with a lot of momentum behind it, right? So that it's just a couple of hours lag between whenever inspiration strikes and when you have something that you can start sharing and demonstrating, and I'll be really interested to see what you guys build with it. Okay, that's I guess that's a wrap. Have a great summer, everyone, and good luck on Wednesday's final.